So yeah, the basic idea is that we want to be able to link this behavior, the behaviors that we talk about in terms of the upstream boundary condition, to what we think is going on in the aquifer, which is really what this is a snapshot of that, and also to what the outputs are at the downstream side, which are the parts on the board which aren't on the screen that we've talked about. And so we know that we have some expression that describes those behaviors. We've actually just scribbled it up on the board, and it is basically this. And so this is the one that we took care of first, so we just had up on the board. The accumulation, the rate of accumulation of concentration of mass at a point is equal to the rate at which it arrives by diffusion or dispersion and removed by diffusion or dispersion, and the rate at which it comes by advection. Nothing more than that. And so if we want to be able to solve this equation, we can. And we can use the solutions from that solution of the equation to be able to say something about what the concentrations might be at our compliance point, which is perhaps something we're interested in doing. The easiest way for us to solve it is to just look at the one-dimensional cases, and those are the ones that we'll deal with first. And so if we're solving this expression, the reason that we get rid of this transverse term here is that if you think about having a system where you have, say, a source that's here that would ultimately kind of look like a plume like this, but then you have a source that's here and a source that's here and here, all the way to infinity in each of these directions, then that makes it a one-dimensional case, so that if you have a little packet of stuff that's being carried downstream here, it's trying to diffuse laterally, but of course it's trying to do it against the packet of stuff that's arrived here from this other source, and so there's some symmetry to it, that the profile would look identical as you go in this direction, in the y direction, And so you only have a one-dimensional problem, and you get rid of this particular term, which is this transverse term. And so what we could do is we could try solving for a simple geometry that includes this differential equation, this PDE, and see exactly what the solutions look like. And so this is the geometry that we're going to choose. And it's a geometry that, of course, if you look, we've just drawn this on the board already, but the geometry basically is if you have your drum here, and this is your pool of stuff that's gone down here, and this is your aquifer which exists here, and this is your well that exists here, then this happens to be the length from the source region to the compliance point, which is the length of this core. There's a velocity, which is an advective velocity along the length of it. And we'll take an x-coordinate that goes through it from upstream to downstream. This point here is x equals 0. This point here is x equals L, uppercase L. And we can try and solve this advection-dispersion equation for that. This is exactly the same expression we just had on the board. And we can imagine a variety of different boundary conditions that we apply to this upstream portion. The one that we have done on the board is just this one where if you look at the concentration changing with time, C over C0, all of a sudden you turn it on at some time and you leave it kept at that magnitude. Bless you. And if this is time, we get some behavior along the length of this sample. Again, relative concentration C over C0, just normalizing it between 0 and 1. And we'd expect it to look like this, where this is length equals advective velocity times time. So nothing more than that. And so the other thing is we know that if dispersion is greater than 0, it'll look like this. and this is dispersion equal to 0. So that's all. And so that's the system we like to solve. So it turns out that there are 3 of these solutions. They're covered in Fetter, and so you can look at those solutions in his book. But the only relevant one for us is the one that we've kind of drawn. We'll deal with 2 of them. We'll talk about the one which is for this Heaviside function, this step function that gets turned on and never goes away. And there's a different solution for the delta function, which is the lower one that's on the board. And so what I want to do is just to demonstrate, well, I guess, so you can solve them. I don't think we need to worry about how we solve them. And so if you solve that system of equations, you get kind of a complicated expression which relies on those boundary conditions. And these are the boundary conditions that we talked about. So the concentration everywhere is initially, no matter where you are, from x equals 0 to x equals infinity, the concentration is 0. Absolutely clean aquifer. The boundary conditions that you apply are the upstream location, where x is equal to 0. This term here, in other words. At time t, and for all times after that, the concentration is just turned on. So that's what this condition is here. It's turned on, it's equal to C0 as soon as it gets turned on, and it stays that way from when it was turned on at 0, time 0 plus, just after time 0, forever. And the other condition is that downstream, at an infinite distance downstream, where x is equal to infinity, then the concentration remains 0, never actually reaches there, which makes sense, right? It has to go an infinite distance, it will never get there, and therefore, indeed, it'll just stay as the existing concentration. So this is basically, these are the initial and the boundary conditions that are applied to solving that equation. We don't need to solve it, we can just use the existing solutions, and in fact, the people who solved this, Ogata and Banks, just borrowed a solution from heat flow, which is exactly the same set of equations to be able to derive their expression. And if you solve it, you get a concentration at some location downstream. The location that you choose downstream is some location L. So in other words, it's here, some distance L downstream. It's for an advective velocity. It's at a given time. It's for a given dispersion coefficient, which is a property of your aquifer, but we kind of alluded to the fact that although it's a property of the aquifer or the plume, it actually doesn't depend on the characteristics of the aquifer, which is kind of a curious observation. And that's it. And this just happens to be a complementary error function, which is a function that we can call up to deal with it. And so that's the solution for that equation. And the solutions for this will look exactly like these if we look at them in space, and they'll look like, if we look at them in time at the compliance location, they will look like this, like this, right? Where this is the time it takes to get there, which is equal to what? I guess advective velocity times time. Advective velocity times time is equal to length over advective velocity. I should always look at the right graph. Yeah. I could do this, can't I? Hold on a sec. I'm smarter than that. Barely. Length over advective velocity. At least it has the right units, right? Length divided by length over time gives you time. And so if you plot out this curve, as we'll do in a second, you'd get that. But let's do something else. The other thing that's useful for us to do is to think about what the controlling behaviors are which kind of modulate this behavior. And so if you indulge me for a moment, let's do something with that expression. So, where are we? It's 3.2, right? Topic 3, 2, I guess I call it quantification. I know you always feel compelled to write this down because you don't know what's coming up. So it's still contaminant transport. So you'll learn that in your past, you've talked about things like dimensional analysis, if you're doing experiments in the lab, you'd like to do as few experiments as you can get away with, but say everything about the behavior of your system. Basically, that's what dimensional analysis allows you to do. And what it allows you to do is it allows you to group parameters in such a way that you can choose the manipulation of the variables you use in experiments to give you the smallest number of experiments that you have to do to be able to kind of fill out your parameter space. And so let's see if we can attempt to do that for this expression that we're dealing with. So you remember, if you look at this 1D expression, it looks something like this. An accumulation term, a dispersion term, which says something about how stuff gets spread out due to mixing, mechanical dispersion, and also how it gets dragged downstream by an advective velocity in the x direction relative to a concentration being carried downstream. And so we know that this relates to our geometry. We know that this is aligned along the x direction. We know that we apply on this face some initial concentration, right? And what else? And we know that we're going to be interested in figuring out exactly what the behavior is at this location downstream, which is some length x equals L downstream. And we also have some advective velocity in here. And also we have some appropriate parameters, which is our dispersion, longitudinal dispersion, right? So I won't cloud things up by writing here the fact that we know that this longitudinal dispersion is a function of both kind of the molecular diffusion, Brownian motion types of things, and mechanical mixing. Oops. Right. So, how do we figure out how we use the fewest number of experiments to describe our system, or for instance, the fewest number of plots that we'd like to make if we're going to graph this solution which we already have here. And so what we can do is we can just start playing around with this expression to do some things. So what we could do is we could divide both sides through by this initial concentration, C0, right? You'll note that the plots that we've already had for this, we've often tended to do these as a function of this relative concentration, C over C0. So that's perhaps a reasonable thing for us to do. Bow, bow, bow. What else might we want to do? Well, we know also that we could relate where we are along this core as some kind of non-dimensional length, right? We could divide, for instance, x by L, in which case this coordinate here would be 1, and this coordinate x over L would be equal to 0. So this is some kind of non-dimensional length along the length here. So to do that, what we could do is, I suppose we could divide this by a length and also multiply it by a length, right? We haven't done anything there. We could divide this by a length squared. And we're just dealing with the dimensions. You know we can do these with differential operators, and also a length squared here. And what else can we do? We could choose to, for instance, divide both sides by this term, which is now velocity divided by length. So nothing we've done has violated any principle of mathematics. So let's now, with my view of foresight, because I've seen the solution, maybe just multiply both sides through by length divided by advective velocity. Right? And so all we're doing is just playing around, nothing. So we can get rid of some things. This and this are there, this and this are there. And so this expression, for instance, if we write this length over L term as a dimensionless length along the sample, we'll call it x sub d. And we can write our expression in terms of a couple, and if, no, let's define these terms. Let's define this term of time multiplied through by advective velocity and divided through by length, which you see here, by the way, right? In Fetter's book, they call this T sub r, just for consistent. And you could call this, if you wanted to, you would call this a Courant number, after the famous mathematician from New York City, the Courant Institute of New York University, not New York City. Let's also define a term which we'll call a Peclet number, which is the advective velocity divided by a length divided by the dispersion coefficient. And we're going to call that P sub e, which is a Peclet number. And so what we could do is we could write this expression out in terms of those properties. And so this would be rate of change of the relative concentration C over C0 as a function of the rate of change of time, but instead of time it's this dimensionless time, which we've included here, which is this. And it's equal to this term here. So what do we have? I guess we have to, okay, I guess I didn't do that very well, because of course if I hadn't been stupid, I'd have realized that this term which we have here has an L squared term in it. So let's get rid of this term here, get rid of this term here, and let's write Peclet numbers instead of this. Let's write it as this over L squared. So it's L squared. So this is just taking this number that we have here, and of course if we do that, then the Peclet number is just the velocity times the length over dispersion. So that was my error. So if that's the case, then this by definition is velocity times length dispersion, so this is just 1 over Peclet number. And we're left with these other components here, which is the second partial of relative concentration. It looks complicated, but believe me, it's not. And the second partial of some coordinate direction dimension all squared. And I guess I should do this. And the only term that's left here is relative concentration, C over C0, divided by rate of change of xd. So that's it. So this is our new differential equation. So you might not care anything about that. But the important things are that now the behavior is governed only by a few behaviors. It's governed by this length parameter, which varies between 0 to 1. It's governed by a relative concentration, which varies between 0 and 1. And I guess we might think that it would look like this at any particular time. And what we might hope is that this represents the plume at some value of TR, that's all, some dimensionless time, and for some Peclet number. So there are really only 4 properties that define this behavior: a relative concentration and how that changes with location. So that's our snapshot in time. But the 2 variables that control the behavior are one which is kind of this non-dimensional time, and one which is this Peclet number, which is, if you remember, who remembers what a Reynolds number is in terms of its definition? Doing that in any of your classes these days? What is it? It's a velocity, a length scale over a viscosity. So does anyone remember what the forces are that are in that? Just out of curiosity. They're inertial forces, whether you're accelerating or not, and then viscous forces. So in the same, that's irrelevant to this class for now, but what's relevant to the Peclet number is it's the ratio, if you write it out as the velocity times length over dispersion, it's the ratio of advective flux. So not a forces, so these are forces. Advective flux to a dispersive flux. So when it's equal to 1, they're about equal. When it's equal to 0, then dispersion dominates. When it's equal to more than 1, then advection dominates. And that's important because it's, I'm kind of digressing, because it also says something about this expression here. Maybe we'll come back to that after I've made my other points. The main point here is that we can describe behavior in terms of just these four quantities, this relative time and the kind of flow regime that we think we're in, whether it's, well, let's write it out. So Peclet number equals 0 is flow in clays and shales, where the flow velocity is tiny and the only important feature is going to be dispersion. And Peclet number greater than 1 is going to be in sands and gravels. Kind of. And that's where dispersion or mechanical mixing is going to be important. But the key issue here is that we can define the behavior in terms of these two variables. So now, the relevance of that is that if we wanted to draw, if I can still keep that there, if we wanted to draw the figure you have on the board for our happy compliance household of an aquifer that sits here, this is xd equals 1, 0. This is time. This is relative concentration. This is 1. And if you wanted to draw, the most important figure that we'll have is this snapshot on the right-hand side. And again, that's going to be a relative concentration between 1 and 0. It's going to be not as a function of time, but as a function of this non-dimensional time. And so our reason for doing that is that some of these plots we'd expect to look like this. For this Peclet number here equal to infinity. In other words, when advective behavior is dominating behavior. And what we find out is that this really represents, what physics, can you think of what a value of this parameter of 1 physically represents? It has a very specific meaning. It basically means that you filled up, so you're injecting stuff at some flow rate, you filled up all the pore space from when you started injection at some flow velocity of this advective flow velocity. You basically filled up all the pore space in this core right up to the end when you get to this value of TR equals 1. So in other words, you turned it on, it was always flowing, but all of a sudden you added dye to it at some relative concentration of C0, and it's physically progressively filled up all the pore space and gone down gradient until you get to this point here, and that's at a relative, at 1 pore volume, basically what would be referred to as one pore volume. And the other important thing which we'll revisit is that we've always drawn the remainder of these plots that they go through a value of 1/2. But what we'll find is that if you look at this, slower values, it turns out that they'll actually look like this. It'll miss this point. So I'm going to just go back so you can see this. This is this figure here. This is out of, you can go back to Feder to get this. You perhaps can't see this very well. 10. Yeah, okay. And so for Peclet, so this is, say, 10. Peclet number 10. And this, stop it. And this is for value maybe equal to 1. And so this is an important plot. Remember, all the other plots that we've done before have been kind of like this. Gone up like this. This is the 50-point mark, 50% mark, and we've had them do this. So I said before that that was a fiction. It's conveniently true for some cases, for large Peclet numbers, but it's maybe inconveniently untrue for cases where it's closer to 1 and below 1, certainly. Right? And so we need to be aware of that. Okay, so the take-home message is that we can recreate this or rewrite this differential equation in some form, and we can use it to get this plot here. The expression for that is, we don't have to rewrite it because you can get it straight out of Feder. This is the dimensional expression, if you like, that gives you a concentration relative to the location downstream, advective velocity, when you want that value, and the time at which you want to take that snapshot. If you get the solution, you could actually rearrange this in the same way using this Peclet number and Courant number. If you non-dimensionalize it, you get a dimensionless concentration, and it's a function of Peclet number and pore volumes or Courant number, and that's it. And so, in other words, you're looking at the behavior. This is written, I guess, for the location downstream where xd is equal to 1. So in other words, x equals L. The end of the core, in other words. And if you plot this curve, you end up seeing that it, importantly, doesn't go through these, this ordinate always. And so this is the right-hand compliance point curve of how concentration changes with time. This is one pore volume, but you can also define this as a time, which is a time times, what is it, a velocity, I guess, over length. And so if you know the length where you're measuring the value, you know the velocity of the flow, then you can calculate what the time is on this axis, nothing more than that. It's relatively straightforward to get that expression. If you look at this expression here, you can take it on trust that this is the value. It's just this complementary error function, square root of the Peclet number over 4 times TR. So you'll start this. Square root of the Peclet number over 4 times TR, 1 minus TR, etc. And so all by ways of just making the point that I think we can do this. So I can't write on this, I suppose, but you know that this is relative concentration on this axis. This is what we're plotting. 1 to 0, C over C0. This is our value, which at the 50% mark, you'd expect that number to go through. And so this is for a Peclet number of 100. So it basically does that. I suppose we could use a bigger number. I guess we can't do infinity, but we could use a larger number. Hopefully this will work. And you get exactly that, right? So you see it kind of sharpens itself as at arrival. This is 0.5 and this is 1. But when you get to cases where all of a sudden the Peclet number is much smaller, maybe why doesn't it want to work? Oh, that's because that's a result, isn't it? So choose a number that's smaller, and I think reset it, then all of a sudden you see, well, it's maybe at 10 we're still there, right? 0.5 and 1. Maybe. So I'd imagine this is the coordinate 0.5 and 1. So it's slightly shifted to the left of it. So physically, what does that mean? It means that if you're expecting that the main plume arrives only after one pore volume has come through your sample, through your aquifer, then you'll be surprised because it got there earlier. And that's a bad thing, right, if you don't want to be surprised. If you look at the case where the Peclet number is equal to 1, where in other words advection and dispersion are roughly the same importance, then you'd be even more surprised if you're basing your calculations on that. Because now one pore volume has arrived, but now you have basically 70% of your concentration is there. The 50% mark, the front that we were assuming before, has arrived after only half a pore volume has gone into the system. And so if you're looking at defining the behavior of arrivals, assuming that it's an advective system and it's a diffusive system, you'll be sadly surprised in an unconservative way, because things will arrive much earlier than you'd think. And so if Peclet number, I guess we can't do 0, but we can do a very small Peclet number. So in other words, where diffusion is dominant, and what do we expect it to look like? Well, let's change the scale here. So now this is just now the peak of the distribution, right? This is 0.99. So this is really just the top of the graph, and it's arriving really early. I don't know how to force it to do it for a full range, but I could just, I suppose I could make this a more reasonable number. So 100th instead of a 10 to the minus 5. And if it plots the whole thing, well, it doesn't, right? This is 0.82 now. And so the important thing to know from this is that these arrivals, which are shown here in this kind of little cameo, progressively occur earlier and earlier as you get diffusion dominated flow. So the one that we drew would be, I guess it would look like this, right? So this is a Peclet number equal to 1 over 10. So you see the progression of these. And so it was fine to use what we used before to be able to do these calculations for arrival times and also what the distribution would look like. But in this particular case, if you're looking at diffusion-dominated flows, not surprisingly, you can't get the proper arrival times by just assuming that it's an advective flow, because it's not. And so beware of that. So I think that's, and there's some discussion of exactly that kind of behavior. So, all right. So these solutions are in Fetter. They're available for a variety of different upstream boundary conditions. We'll only really use the one that we talked about, so I'm not going to go through the other boundary conditions. There's also one for this pulse injection, so this kind of delta function. And again, you get some relative concentration. This is just C over C0, basically, as a function of Peclet number, pore volumes, and another term which is again a function of pore volumes and Peclet number. So I don't think we've traditionally rarely used that in this class, and so I'm not sure that we need to belabor that point. Okay, so we said that when we entered into this that we talk about a couple of things. We talk about what this advection-dispersion means, equation means in terms of these one-dimensional flows, and also in terms of 3D flows. So let's quickly just talk about the behavior for 3D. That's where we'll leave this. And so the idea is this. So you take a bird's eye view of your site, and all of a sudden at time 0 you put some stuff in the ground, or some stuff goes in the ground. And you know that you have a flow field that's in this coordinate direction where the velocity is in the x direction, the velocity in the y direction is 0. There's some advective flow velocity which is driving flow. And you'd like to be able to say exactly what the plume looked like at some later time. And so the solutions for this are derived from these advection-dispersion equations also, but we'll just quote the results and kind of say what the results represent. The results basically are a bell curve. And so if you looked at kind of drawing a cross-section through this line here, this is a plan view, right? So this would be kind of the outline of the plume as it's gone down gradient. And if you wanted to put a contour that included almost all of the mass of the plume, it would be this external contour. But if you plot it versus relative concentration, C over C0, then the plume might look something like this, or the distribution would be a bell curve, Gaussian distribution. And so what it is basically, we talked about this analog last week, the idea of advection. You take a beaker, you drop a drop of ink in the water in the beaker, and you march across the room. If there's no dispersion, then that drop of ink will look like a drop of ink once you get to the other side of the room. If you do the same, drop it in, but you allow Brownian motion or dispersion to occur as you move across the room, then by the time you've got to the other side of the room, what it will look like is it'll look like this, it'll have gone from looking like Manhattan at this point here, right? Simplistic view here of Manhattan at this point, to spreading out. And so what we're doing is we're just going to solve the expression for dispersion and physically translate the coordinate system some point downstream. That's what we're doing. And so this expression here is one that is for a Gaussian distribution. That's all. This is the location where you find yourself at any particular point in the plume. This is the location where you dumped it into the aquifer, x0, y0, z0. The coordinates where you find yourself are x, y, and z. The time at which you want to know what the plume looks like is time t, and it has dispersion in the longitudinal direction and in the transverse direction. And of course there are two transverse directions because this is kind of an ellipsoid that is spreading out not only in plan view in the y direction but also up and down in the aquifer as well. And so this is basically the equation of an ellipsoid, if you like. You can recast it, instead of in these coordinates, relative to this kind of center of mass. So the center of mass in a given time has moved in a length L equals Vt downrange, right? This is the advective velocity. This is the time since it was dumped into the ground. And so the center of mass of this cloud has moved this length downrange, and this is where the maximum concentration would be in the middle. And so instead of using these coordinates, you could just choose coordinates relative to this, this moving coordinate system, which is centered on the center of mass of this plume. X, Y, and Z relative to that. And this is the concentration. And so you see in here we don't have a relative concentration C over C0, because it's defined in terms of the mass of solute that's been put into the ground. So this is the mass of solute. And I suppose you could tell me is it mass? I guess you could. We could check that from the dimensions, right? So this obviously is an exponential function, so it has no dimensions. And so if you take, for instance, x equals 0, y equals 0, and z equals 0, so in other words, this case here, then the exponential of 0 is 1, and so the maximum concentration is in the center of this distribution, as you could already surmise, and it falls off to the sides from this. And so can we calculate? I suppose we could check what this is dimensionally homogeneous, right? It doesn't mean that necessarily the equation's right, but we know that if it's dimensionally inhomogeneous, it has to be wrong. And so if we do just the quick calculation on, what's this, kilograms is for mass, T to the 3 over 2 is seconds to the 3 over 2. And what's this? We said that this is in meters squared over time. So this would be in meters squared cubed, so I guess that's meters to the 6 over time to the 3rd. and those are the only dimensions we have in there. And so this would be in units of, does it work out? Oh, yeah, I guess, but to the half. So if this is kilograms over seconds to the 3/2 multiplied by meters cubed times seconds to the, so this is seconds to the 6th, is it? Yeah, but it's 1 over, right? So it's minus 3/2, is that right? So this is seconds to the minus 3/2, is that right? Sounds like that cancels out. That shouldn't happen, right? So this is concentration for sure. Yeah, that's right. It cancels out. It has to, right? So this is mass per unit volume, which is concentration. And this is T to the 3/2, T to the minus 3/2, just because this is 1 over. And so it's in units of kilograms per volume, meters cubed, which is concentration. So it doesn't necessarily mean it's right, but we know it's not necessarily wrong. That's worthwhile knowing. And so physically what that looks like, if you look at this behavior, is as you go downrange, then this is just kind of a spreading plume. And so at time t0, when you introduce this, it's at a point, in theory. At some later time, it's spread out, and at some later time, it's spread out more. And the important features are, if you draw some kind of bounds around this, where this is basically the furthest extremities, if you like, of this distribution, then it would look like this Gaussian distribution. And we know, we talked about this a little bit when we last week, I guess, on Tuesday. This is Tuesday, on Thursday, I guess. About the fact that one standard deviation was, what, 34%? 1 sigma was equal to 34% of the distribution. 68 if you take both sides. And if you take 3 standard distributions, it actually includes basically all the distribution. So the 3 standard deviations in this particular case is equal to the cube root of 2 times dt, or rather 3 times the square root of 2 times dispersion times time. So for instance, if you could take a snapshot of this plume at a given time as it's gone downrange, and you could measure how big this is, how large this standard deviation is, then you know this. You know when you're taking your picture of it downrange, and you have a way, for instance, of being able to calculate what your dispersion is. Alternatively, if you knew what your dispersion was, and you knew when it was you're looking at your plume, you could calculate what the size of this was as well. So the two methods. I guess the second method is probably the most important one if you want a predictive sense of what your plume looks like. If you actually have a plume and you want to calculate what your dispersion coefficient is, you could do it the other way around. But that's basically the behavior for looking at a three-dimensional plume, if you like, as it goes downstream. So we've covered two basic methods of doing that. So the other thing, well, that we could use that for, since we've kind of gone through the things that we wanted to talk about, is we've talked about both of these behaviors, both for kind of a one-dimensional flow, which was just our standard core, which we're using to look like our aquifer, and also the three-dimensional case was just this distribution that slowly spreads as it goes progressively further downrange. And so relatively simple expressions, don't need to know how to solve the differential equations, but need to know how maybe to be able to use the solutions once we have them. And so we can just use these expressions directly. And you'll get some chance to use that. So really the important material that we talked about, the results that are basically on this page in being able to look at, for instance, this distribution at the compliance point. And of course, if you wanted to, you could, I suppose, choose different lengths. So the other thing that you could plot if you wanted to is you could plot for different lengths along the plume, you could choose a length of this, and you could calculate the concentration at a given time, and you'd get some concentration magnitude here. Choose a different length, you'd end up with a different one. And basically, you could also reproduce the curves in terms of relative concentration that you have in space rather than in time in your compliance location. So nothing more than that. So that's it. So I'll leave it at that for today. So the important thing is being able to, I think, understand physically what's going on in terms of these behaviors, as we started out chatting today. Understand, I think, that there's an expression that governs that behavior, which we know something about, and if we wanted to, we could solve, and as a result of that, we get some responses, and the really key important piece of these responses is this diagram here, and the fact that this does not necessarily go through this center of mass of the plume, as we've kind of assumed up till now. And if you want to kind of reconfirm that in your own minds, you can either plot these expressions here, or you can go back to Feder, and you can look at this, the equivalent of this figure here, which comes from Feder, which is a bit garbled, but if you draw out the curves, this is relative concentration from 0 to 1. This is this pore volumes from the pore volume of 1 is the important one, and it's the solid curves which represent the particular boundary condition that we looked at here, which is for a Peclet number of 100, a Peclet number in this particular case of 10, and a Peclet number in this particular case, I think, of 1, and of course a value of 0.1 I think would look like this, 0.1. And so no longer do we assume that the values all go through a curve that looks like this. So we need to make that change. Okay? All right. So that's the main takeaway point from today.